Okay, we're almost done with section 1.8. Just want to go over a couple other things, a couple other little strategies you can use when you're writing proofs. So one is to proof by cases. So the idea of proof by cases is if your hypothesis, satisfies one of two or three or four different possible propositions like P1 or P2, and that implies Q, this is actually equivalent, and you can prove this, with just logical equivalences. You can show that this is equivalent to P1 implies Q, or P2 implies Q. All right. So essentially, what this means is that you can say your hypothesis breaks down into several cases. You can say, okay, case one, let's prove, if P1, if assuming P1. Then you can deduce Q. And then case two, you can say, let's prove if P2, right? So we'd assume P2, well then we can deduce Q. So that's what I did on the example when I was showing the example with the square roots of 2 all over the place, right? Showing that there exist the irrational numbers, that one raised to the power of the other is rational. I ended up breaking that down into cases because our statement that we wanted to have what we were working with here, this idea of square root of 2 to the power square root of 2, that satisfied one of two possible propositions. Either it's rational or it's irrational, right? So hence two cases. It doesn't have to be two cases because this actually extends to any number of propositions in this disjunction over here. You can have P1 through P5, and it breaks down into 5 different possible cases, right? Now, if you have an infinite number of different possible cases, well, then it doesn't work because you can't do an infinite number of different possible cases, right? Like you can't do that. And in general, even if the number of possible cases is like thousands, then it's just not a feasible way to write a proof. You don't want to have to deal with thousands of different individual cases in your proof. Probably. Although, modern proofs these days, especially computer-aided proofs, which are a big thing these days, they do sometimes deal with mind-boggling number of cases. So anyway, I won't do an example of that because I kind of included it already in an earlier one, and it's pretty straightforward, the idea. There's another strategy I want to explain in this video, which is something called WOLOG. So WOLOG is an abbreviation for without loss of generality. So this is used when you have, I would describe it as, it's used when you have symmetry. When it's like A and B, maybe like one of them is integer, or one of them is positive and one of them is negative, or one of them is rational and one of them is irrational. And it's like, well, there's symmetry here. You could have A be the positive one and B be the negative one, or A could be the negative one and B could be the positive one, and it basically would be symmetrical. Like you could swap them and nothing would really change besides what letter you're using. And in situations like that, you can say, well, without loss of generality, let's have A be the positive one and B be the negative one. And so that is common enough in proofs that mathematicians decided to come up with an abbreviation for it. So sometimes you'll see WOLOG in a proof. I'm going to show you a little example of a proof that uses that. So the example is going to be, we're going to show that 5x plus 5y is an odd integer whenever x and y are integers with opposite parity. What's parity, you may ask? Parity is the property of being odd or even. That's what parity is. So the parity of an integer is its oddness or its evenness. Kind of like how you talk about the sign of an integer, that is its positive or positiveness or negativeness. Sign, positive or negative. Parity, odd or even. So this is a perfect sort of a situation for WOLOG because all we want is to assume that x and y are integers with opposite parity. And it doesn't matter which one is which, really, because check it out. If you were to take 5x plus 5y and swap the x and the y, then you would still have 5x plus 5y, right? Because you could just change the order of the addition with the commutative law. So we'll begin the proof by saying, let x, y be elements of the integers, and then WOLOG, without loss of generality, let x be odd and y be even. Great. Then that means x is going to be, what are our definitions of odd and even? Well, odd means 2k plus 1 for some integer k. And then y is going to be, what is our definition of even? It's 2 times an integer. I can't use k, though, because I already used k. And it's not necessarily going to be 1 less than x, right? That would be that'd be a faulty assumption to assume it's just 1 less than x. No, it could be a different k. So let's we're not going to use k again. Let's use L. Last time I was in this situation and I couldn't use k, I decided to use L. So let's let y equal 2L again for some integer L. Okay, so now let's look at 5x plus 5y, right? We've got our assumption. You know, we've got one odd, one even, and we've stated that what that is in terms of k and an L. And so now 5x plus 5y would equal 5 times x. X is 2k plus 1. Plus 5 times y, which is 2L. And I get, doing a little algebra, 10k plus 5 plus 10L, which is going to be 10 times k plus L plus 4 plus 1. And I'm running out of space a little bit here, but so I'll just kind of shift this up. If you take the 10 and the 4, those are even numbers, and we got this plus 1 on the end. By the way, how did I get plus 4 plus 1? I just took the 5 and I broke it into 2 pieces. That's all. Super easy thing to do, but something you might not think to do, right? But keep in mind that you can do super basic things like 5 is 4 plus 1. And that's actually helpful here because it means we can factor a 2 out of the rest of it. Like that, right? Bring it down to this. And so now, since that part in there, the 5 times k plus L plus 2, since all that is an integer, this shows, in fact, that 5x plus 5y is actually of the form 2 times an integer plus 1, which is the definition of being odd. So which shows 5x plus 5y is odd. And that completes the proof. So that's an example of using WOLOG. Now, if I hadn't used WOLOG, then technically what I would have needed to do, like if you weren't relying on this like built-in symmetry to the problem and weren't sort of appealing to that with the without loss of generality statement, if you're not appealing to that symmetry, technically you would need to have 2 cases, one where x is odd and y is even, and then a second case where x is even and y is odd. But the proofs in the 2 cases would look pretty much identical, right? It would look almost exactly the same, except these terms would be swapped around. But of course, addition is commutative, so why should we bother doing the work of proving it twice when it's almost the same both times? That's what WOLOG is for. Don't be careful not to overuse it. You don't want to overuse WOLOG when there is a substantive difference in the 2 cases. You only use it when they're perfectly symmetrical with one another, and it would be stupid to write them twice because all you'd be doing is writing them with different letter names or something like that. Okay, so be a little careful, and of course, if you're ever unsure as to whether or not you're allowed to use WOLOG or whether you should use WOLOG, just go ahead and ask, and I'd be happy to offer advice on that, even if it's during a test. That's the kind of thing I'm happy to give some advice on, because it's a little loosey-goosey. I think that's all I'm talking about for section 1.8. So I'm going to wrap this up and post these last few videos.